Hello there. It's nice to share this quiet with you. The evening has settled like a light blanket, and your breath moves in and out without trying. Nothing asks for you now. Nothing leans or hurries. Just a gentle voice, a room at ease, and the night resting its calm hand on your shoulder. Tonight, we'll listen for the smallest sounds in nature, the whispers of the atom. Not a lecture, not a rush. We'll drift softly from the glow of a bedside lamp to the hidden motions inside it. Electrons humming, bonds loosening and holding, tiny particles shaping warmth, memory, and the light on your wall. We'll visit the atoms in your tea, the iron in your blood, the stardust in your bones, and let their quiet patterns rock us toward rest. If this slow journey brings you comfort, a gentle like and a soft subscribe, help others find this peaceful corner too, only when it feels right. For now, let your breath lengthen, let thoughts unclench, and let the small world within you settle like snow in a calm globe. Close your eyes. The tiniest things are speaking, and we'll follow them together, unhurried and warm. From sandals on stone and scrolls unrolling under the Mediterranean sky, to equations by lamplight and magnets humming in the dark, the path is long but gentle. More than 2,000 years of wondering and testing have carried a single question across the centuries. What is everything made of? No lab coats here, no alarms, no urgency. Just a slow breath and a soft curiosity as we follow the trail of tiny things, too small to see, yet steady enough to hold up the whole world. This is for relaxation and learning, a quiet companion for the night, never a substitute for medical care. Let the caution sit at the edge of the room. The rest can be soft. Long before microscopes and accelerators, there were people leaning on railings to watch the sea. They argued beneath olive trees and traced ideas in dust. About 25 centuries ago, Greek thinkers asked questions that still feel fresh when you whisper them in the dark. If you keep breaking a stone half, then half again do you reach a last grain you can't divide? If warmth fades and returns, if a cup breaks and is mended, is there a smallest something beneath all the changes? A bit that does not surrender? Two names glimmer from that time, Leucippus and his younger, more famous student, Democritus. Their answer was quiet and radical. Yes, they said, there is a smallest piece. They called it atomos, uncuttable. Not a poem, not a metaphor, but a claim about how the world is built. These pieces, they imagined, were solid and enduring, different mostly in shape and motion. Some smooth, some hooked, some heavy, some quick. By joining and parting, by colliding and tumbling through space, they made stone and water, flame and flesh, bread and bronze, and the memory of a summer afternoon. To make room for their tiny travelers, they also asked for something many found unsettling: the void, empty space, a place with nothing in it at all, so that atoms could move. To modern ears, this sounds ordinary. Of course, there is room between things, but to many in that age, it felt indecent, as if the universe were being thinned beyond courtesy. Nature, people said, abhors a vacuum. Democritus smiled and kept going. He treated the invisible as a real country. He even suggested the soul was a fine, swift arrangement of special atoms, round and nimble, moving like small sparks through the body. The world, he believed, could be understood without a hidden puppeteer, matter moving in simple open space, forming patterns we could learn to read. This was not only physics to him, it touched happiness. Align the mind with how things truly behave, and contentment would have a place to sit. Not everyone was charmed. Plato preferred perfection to particles. He loved clean shapes, living in a brighter realm, ideal forms that the world only imitates. The idea that everything could be reduced to tiny bodies in motion felt too coarse for his taste. Aristotle, whose voice would echo for nearly 2 millennia, went further. He denied the void and replaced atomos with qualities. He spoke of earth, air, fire, and water, 4 basic natures shaped by hot, cold, wet, and dry. In his universe, change was not a shuffle of little billiard balls, but a steady drift toward natural places. Fire rising, earth settling, water flowing downward in patient obedience to its temperament. It was elegant, teachable, and most importantly, preserved in tidy texts that copyists loved. Democritus's works, by contrast, drifted out of reach as the centuries turned. We know him mostly through quoted fragments, sometimes saved by people who argued with him even as they recorded his lines. Even so, his pictures linger. Dust in a sunbeam, spinning and weaving. Looks like what he imagined atoms might do, always in motion, always combining and parting, shaping the flavor of honey, the bite of salt, the hardness of iron. He guessed that differences in material came from shapes and arrangements. He had no microscope, no chemical table, only reason and a patient imagination. Yet imagination, when it sits quietly with the world, can land close to the mark. The seed was planted. It simply needed light it would not receive for a long time. For nearly 2,000 years, the atomic idea slept in public. It did not die, it dreamed. Meanwhile, other stories about matter took the stage, stories that blended hands-on craft with symbolism, recipes with stars, fire with prayer. Alchemy grew in many places at once, in the workshops and courts of the Islamic world, across medieval Europe, in China and India, wherever curiosity and need shared a table. It was a practice as much as a theory, and often a pilgrimage. Metals were melted and hammered. Glassware blossomed into coils and bulbs. Vapors were coaxed through tubes, then welcomed as drops into waiting cups. The goals were many: to purify, to heal, to extend life, to touch gold, to understand what lived beneath the skin of things. It is easy to smile at the wish to turn lead into gold. But inside the wish is a sane thought. Matter transforms. Wood becomes ash and smoke. Grapes become wine. A mineral yields its color to a dye bath. In the absence of atoms, people spoke of essences. They drew delicate diagrams and wrote in layered symbols. Metals were paired with planets, days with moods, colors with temperaments. Underneath the myth, the hands kept working and the eyes kept watching. The air of a laboratory, smoky, vinegar sharp, sometimes sweet, sometimes alarming, held a stubborn truth. When you heat this, it rises. When you cool that, it hardens. When you mix these two, the liquid clouds and then clears. Slow, careful craft, steps repeated, outcomes compared. Language, yes, but also practice. The old 4 elements remained a favorite map: earth, air, fire, water. Not particles, but behaviors. Dryness, dampness, heat, and chill were how things declared themselves. A loaf was mostly earth with a hint of fire. Steam was a soft marriage of air and water. Wrong as a picture of atoms, the map was useful as a way to notice and predict. Without instruments to peer deeper, it offered a flexible way to talk about change. People applied it broadly to weather, to medicine, to moods, and felt a pattern holding. It soothed the mind to imagine the world balancing itself. each thing drifting toward its rightful share of heat and moisture, each illness a misarranged quartet seeking harmony. Aristotle's refusal of empty space helped keep atomism off the main road. In a world that admits no void, there is nowhere for tiny bodies to fly unhindered. Scholars copied his books with care. Shelves that survived storm and moth tended to be his, and so the conversation leaned toward continuous matter qualities, spreading without gaps. Invisible particles felt too sharp, too mechanical, too cold. Better to think in textures. Yet while the official story walked that path, people were quietly building a new language with their hands. In the Islamic Golden Age, the figure the West calls Jabir ibn Hayyan, Jabir for short, helped turn alchemy into a system. Distillation was honed, crystallization made finer, evaporation guided with a steadier hand. He proposed that metals were blends of principles like mercury and sulfur, wrong as physics, but closer to the idea that different materials have distinct inner balances. His notebooks multiplied techniques, refined apparatus, and named acids and salts with growing confidence. The laboratory was learning to be a place where the same action yields the same result, a quiet revolution made of repetition. Across Europe, a physician named Paracelsus carried the lab into the clinic and argued that careful preparations could ease illness. Instead of chasing wealth alone, he chased remedies. He added salt as a philosophical third alongside sulfur and mercury again, not the table seasoning, but a symbol of body and fixity. He spoke in a voice workers could hear, not only scholars. Fire and glass moved closer to the aches of real people. Glassware improved. Furnaces breathed steadier. Artisans learned to keep smoke out of the way and keep notes in a safer place. Crucibles cracked less often. Time entered the laboratory in a new way. Minutes counted, hours watched. The rhythm of heating and cooling held like a song. In margins and ledgers, properties were listed. Sharp smell, sour bite, green flame, violet flash, heavy residue, clear distillate. Without atoms, the mind still groped toward organization. What dissolves in what? Which metals yield to which spirits? Which colors are born when two clear liquids greet, and suddenly cloud, then clear? All the while, the four elements kept offering a net for the imagination. A physician could describe a fever as excess fire and imagine a draft that lends water and calm. A blacksmith could speak of a metal's temperament, how stubborn it was, how likely to run or to hold and not feel he was only guessing. The language carried feeling and instruction at once. And yet, in smoky corners, the idea of building blocks flickered. If you said, "Perhaps there are smaller things inside," someone would ask, "Where would they move if there is no empty space?" The old answer, "In the void," was not welcome. Still, the itch remained. A steady change prepared the ground. People began to sort. Cabinets of wonders held shells, minerals, and small bottles side by side. Apothecaries kept careful drawers for powders. Miners compared ores from different hills and noticed how one vein smelted sweeter than another. Dyers learned which mordants fixed color best. Brewers discovered the temperature at which yeast felt at home. All of this was local and practical, knowledge that respected hands and noses. But it built a scaffold for thought. When a later mind reached for a general rule, the facts were waiting. The comfort of continuity began to feel a little stiff. A bell jar lifted from a bowl of water made the water climb the glass. If the world disliked emptiness, the picture fit, but new tricks would soon test the idea. Before those tricks, the belief held. Space did not tolerate absence. Air slid in to fill the gap, or water rose, or something subtle balanced the accounts. There was peace in such a universe. No holes, no breaks, everything touching everything else, a quilt rather than a mosaic. Meanwhile, Democritus survived as a rumor with a smile. He had argued that sweetness and color were not in things but in us, that what we feel is the mind's way of greeting shapes and motions too small for our eyes. It sounds modern even now. The idea did not win the day, but it refused to vanish. Even in commentaries that rejected him, a line here and there preserved the atom, a seed folded into parchment and laid away. Workshops grew busier, tools became a little better, alembics sealed more tightly, balances weighed a little truer, acids learned to knock politely at the doors of metals and ask them to come out. Painters learned which pigments would darken, which would stay bright, which would poison. Soap boilers, glassmakers, tanners, and gilders refined their crafts until results could be counted on. In that slow accumulation, the atom's silence became less comfortable. If mixtures behaved so reliably, if a substance always broke into the same proportion of parts, perhaps those parts were real. The thought hummed beneath the music, not loud yet, but steady. Return for a moment to the human side, the one that isn't a ledger, but a pulse. An alchemist at dawn, watching the first color change in a small retort, was not only chasing gold. A deeper wish was at work, to understand what lives inside matter, to bring the hidden into reach, to be a partner to transformation rather than its surprised witness. It is the same wish that drove Democritus to imagine smallness and space. It is the wish that drives a baker to learn exactly how warm the room should be for dough to rise. It is a patient, domestic longing for order, not the strict order of a drill sergeant, but the reliable order of sunrise and tea. So the atomic picture rested, not erased, just set aside. In its place stood a universe of qualities, hot and cold, dry and wet, bitter and sweet, heavy and light, each leaning toward its own balance. Physicians spoke of humors, kings kept astrologers, and philosophers wrote careful pages about causes and purposes. Against that warm weave, the idea of little bodies flying in an empty nothing felt harsh. You can forgive them for not welcoming it back. And yet, here and there, the night gave hints. In handwritten pages, someone listed the weight gained by a metal after it had been roasted in air, and the numbers repeated. In a workshop, a jar of acid always behaved the same way, with the same filings. In another town, a simple pump seemed to coax a little silence into a glass vessel and make a flame falter. Laws were not yet written, but patterns pressed forward. You can sense the world leaning toward a new account, as if the furniture of the mind were being nudged inch by inch into a different room. Across regions and languages, a quiet confidence grew. Substances have character, and character persists. If you purify a mineral carefully, it melts in a narrow band of heat. If you combine two clear liquids in a certain order, the cloud that blooms will often clear again. If you add just so much more, someone wrote those thresholds down. Someone else tried them and got the same results. A braid of practice and memory tied one century to the next. What began as speculation beneath an ancient sky would return not as a thunderclap, but as patient housekeeping. Glass made truer, balances made tender, flames held steady, language gently untangled. Then came laws of proportion and gases, names gathered into families, and at last the plunge inward electrons, nuclei, the whole restless crowd. That is for later. For now, it's enough to feel how the ground was prepared. Think of the centuries as one long, careful inhalation. Sandals and scrolls, furnaces and flasks, bronze mortars, ink-brushed fingertips, a student at a window watching air cool the glass, a teacher wiping ash from a crucible's rim, a merchant packing a cabinet of minerals for a slow river journey. Each small act of attention nudged the world toward a clearer image of itself. You can sense the gentleness of that labor when you rest your hand on a warm teapot and understand without a lecture. Heat moves, water carries, metal takes on a shine when the fire is right. Inside those everyday truths, an old whisper kept its shape. Everything large is woven from smaller things, moving and meeting in patterns the heart can learn to trust. So the atom waited. It slept in manuscripts and cameos, in jokes about the laughing philosopher, in the way dust behaves when a blade of sunlight slips through shutters. It slept in a brewer's tidy ledger, in a physician's cautious note that a certain tincture often eases a certain ache, in a tinkerer's diary of weights and measures that no matter how he tried to bend them, refused to lie. It slept, but it never left. And when the right hands built the right tools and the right eyes stood before them, the old uncuttable stirred, stretched, and stepped back into daylight as if it had only been resting, waiting for us to be ready to hear it clearly at last. Imagine leaning closer to the night and asking softly, what if everything really is built from tiny, unseen pieces? By the 17th century, the old picture of earth, air, fire, and water had begun to fray. In chilly rooms lit by candles and morning windows, people warmed metals, trapped vapors, sealed vessels with wax and string, and sometimes learned the hard way which mixtures prefer to sleep undisturbed. Curiosity kept easing the door open. Among the most tempting mysteries was the air itself, the quiet, invisible ocean around every breath. Was it a kind of nothing, or did it carry its own secret weight? From that gentle question, the path into proportions and gases, and eventually, deeper into the atom, began to open. An Irish natural philosopher named Robert Boyle stepped into that question with a calm stubbornness that suited the work. He liked careful instruments and clear notes. He tolerated smells that would empty a parlor. With his friend and collaborator, Robert Hooke, sharp-eyed, endlessly inventive, he built air pumps that could worry the breath out of a glass vessel and leave behind a space thinner than anything most people believed could exist. For centuries, Aristotle's voice had hovered over the conversation, insisting that nature hates a vacuum. Boyle listened, then turned the crank. The room taught its lessons quickly. When the air inside the bell jar was drawn away, a candle's flame guttered and died. A small creature placed under the glass faltered, then fell still, while a second creature under ordinary air continued without distress. Sounds became strange, faint, then all but vanished. Whatever this surrounding substance was, it acted, it mattered, it carried life on its back. It was not nothing. Piece by piece, a new picture gathered. Air could be compressed and released. It pushed outward, it pressed downward. Treat it as a crowd of swift little bodies moving in every direction, and the pressure in a vessel becomes the touch of their collisions on the walls. Give them less room and they strike more often. Give them more room and they strike less. The idea was simple enough to explain at a table and strong enough to hold under experiment. Out of that steadiness, Boyle wrote a rule. If the temperature stays the same, the pressure of a gas is inversely related to its volume. Halve the space, and the pressure doubles. Let the space expand, and the pressure drops to match. It was a sentence about the behavior of hidden things that could be tested over and over with valves and glass. and patience. What made the work different from the old talk about elements was not only what it said, but how it was learned. No appeal to essences, no arguments sown from metaphor alone. Instead, glassware that hissed and sighed, mercury creeping up and down in tubes, balances tilting by small, stubborn amounts, the same results, greeting the same steps on different days. The invisible began to feel real because it obeyed, because it answered the same way when asked the same question. Hook deserves his own chair at this quiet table. He improved pumps until they could pull a finer emptiness, then asked what that absence did to plants, to insects, to sparks and smoke. He suspected that something in the air was required for flame and for breath alike, a hint of what later chemists would call oxygen. His mind ranged easily microscopes and springs, buildings and fossils, but in the world of gases, he returned again and again to a simple tenderness. Living things need whatever is present in clean air and absent when the pump has done its work. A sense of theater threaded through these demonstrations. Imagine a dark hall, a bell jar on a polished table, a circle of faces lit by lamps, and the small bravado of experiment. Air captured in a bladder rests on one side of a balance. The scale dips. Another bladder, emptied by the pump and sealed, hangs on the other side. The arms find a new level. Weight, the audience murmurs. The weight of what we cannot see. The lesson was gentle and firm. Invisibility is not the same as absence. Boyle's instincts carried him away from the ornate language of alchemy. In a book with an honest title, The Sceptical Chimist, he questioned the old talk of 4 elements and proposed that substances might be built from small, material corpuscles, arranged and rearranged. He could not see these pieces, but he could feel the tug of their logic in the numbers, the pressures, the repeats. It was not yet the atom of today, but it was a hand stretched in the right direction. The 17th century gathered other instruments around this airborne revolution. Barometers rose and fell with weather. Thermometers offered numbers to warmth. Sealed flasks became tiny worlds where rules could be traced without interruption. Language shifted beside the glass. Instead of hot and dry or cold and moist, notes began to read 1 part to 2, volume halved, pressure doubled, flame extinguished at such and such a height of mercury. The mind had found a different rhythm, still human, still curious, but walking now to the beat of measurement. From this steadier ground, the story moved toward a Parisian courtyard, toward polished copper and paper labeled in a careful hand. Antoine Lavoisier lived there, organizing matter as a librarian organizes books. He was not chasing gold, he was weighing. He built a laboratory that breathed order, balances so sensitive a grain of sand could tip them, vessels that could be sealed so tightly that nothing escaped uninvited, burners that delivered heat the way a violinist delivers a note cleanly, repeatably. His wife, Marie-Anne, sketched apparatus with clarity, translated papers with precision, asked questions that sharpened the work. Science, in that house, looked like sunlight on metal. At the time, a fashionable picture claimed that combustible things contained a subtle principle called phlogiston. When a substance burned, it was said to simply release that principle into the air. If the world behaved strangely, if a calx, the ash-like residue from heating a metal, weighed more than the metal itself, the defenders of phlogiston replied that perhaps phlogiston had negative weight, a lightness that turned numbers upside down. Lavoisier stood at the balance and let the weights speak. He heated metals in closed vessels where he could weigh not only the solid but the air that bathed it. Over and over. The story repeated. The metal gained mass as something from the air was captured. The air inside the vessel was left poorer by exactly the amount the metal had gained. No disappearing spirit. A union, not a loss. From those clean sums, he shaped a principle that now feels like bedrock. In chemical change, matter is conserved. Nothing is created or destroyed. It moves, it rearranges, it recombines. Burn a log, and the room fills with warmth and smoke, the grate with ash. Gather every breath of gas and every flake of soot and set them on the scale with what remains of the wood, and the numbers will match the beginning. The world, in its transformations, keeps its accounts. Names became clearer under his pen. Instead of a forest of private symbols and local phrases, he pressed for a shared language. Substances were not essences, but elements and compounds. Reactions were not riddles, but equations that could be balanced. He helped identify the character of oxygen and hydrogen, described nitrogen as a distinct presence in the air, and fit them into a simple bookkeeping that let students see at a glance what combined with what, in what proportions, to make which new thing. A textbook emerged, tidy and spare, that carried chemistry out of charm and into clarity. It did not banish wonder, it made wonder testable. He still made human mistakes. He thought oxygen sat at the heart of every acid, an idea later shown to be too neat. But the method was the point. Observe, measure, repeat, trust the scale over the story. Let the experiment correct the pride of a bright guess. In that method, an entire field straightened its shoulders. Beyond the laboratory walls, the streets grew louder. Paris reshaped itself under the pressures of revolution, and Lavoisier's work as a tax official painted a target on his life. The same careful hands that adjusted small weights on a balance could not steady the larger currents of history. In 1794, he was condemned and executed, a loss that still stings across the years. A mathematician who admired him murmured that the blow took a moment, but a century might pass before the world raised another mind like his. The laboratory dimmed, then filled again with other workers who kept his habits alive. What he left behind mattered to more than chemists. He left behind a feeling. The world is legible if you ask it well. Weigh the air, count the gas. Capture the smoke you once thought was nothing, and discover that it is something exact. Watch a metal grow heavier as it drinks a portion of the air. Then prove that the missing air is the same portion each time the process is done cleanly. Replace charms with measures, secrecy with shared terms, and rumor with a sketch of glass a stranger can copy. Together, Boyle's steady hands and Lavoisier's tidy mind drew a path from the old elements to a leaner map. Matter as a crowd of small entities that move, that press, that join, that part, that keep their ledgers tidy, even while flames leap and colors bloom. The experiment with an air pump that made a candle fail is not just a trick, it is a way of saying the unseen has rules. The balance that tells you the ash weighs more than the metal reminds you gently that your eyes alone can be fooled by change. The law that pressure doubles when volume halves is a lullaby for hidden motion, a promise that if you give those unseen pieces less space, their hurried taps on the vessel will grow more insistent. In rooms far from Paris and Oxford, artisans felt these changes in their hands. Soap boilers learned to count. Dyers measured not only shades but weights. Glassmakers tamed furnaces with thermometers. Physicians began to ask what portion, not only what potion. A slow shift carried craft toward science, without stealing craft's humility. The best discoveries still began with attention, a flame flickering oddly in a jar, a powder changing color a moment sooner than yesterday, a drop of clear liquid clouding at a precise measure, then clearing again when just a touch more was added. This new way of looking did not kill the old wonder, it taught wonder a steadier walk. Air ceased to be a single mystical element and became a congregation of gases with distinct behaviors. Pressure could be coaxed higher or lower, traced with a finger along the curve of a gauge. Heat stopped being an animal spirit and became a number on a slender glass stem, an amount you could point to with a fingernail. Words softened and sharpened at once. Instead of saying a substance was light or heavy by feeling alone, the hand passed its judgment to the scale and let the digits speak. Once people understood that even a breath could be weighed and divided into parts, curiosity turned inward with more confidence. If air has pieces, what of water? What of metals and salts? Might there be a grammar that all matter shares, a set of letters that spell wood and stone, skin and smoke? The atom, still unseen, felt closer, not as a dream, but as a practical convenience the mind could no longer do without. Imagine that every substance is built from small units. Write the equations that way. Discover that the numbers behave. The model earns its keep by making the world easier to predict. Stand for a moment in Lavoisier's bright laboratory and listen to the room. A thin flame holds steady under a vessel. A valve taps, a balance arm settles. Somewhere on a shelf, a notebook waits with a date written at the top and a line drawn beneath it with a patience only habit can teach. The night outside is full of voices and weather and change, but in here the air is portioned and named. The reactions proceed under watchful eyes, and the same small claims become truer with each retelling. Mass in, mass out, gas taken, gas given, names that stay put. A language you can hand to a student without apology. The story carries a tender lesson fit for a bedtime hour. The smallest things are not only elusive, they are also faithful. Treat them carefully, and they will show you the same face today and tomorrow. They will let you press them closer or give them room, and they will answer in kind. They will pair off and part again according to quiet habits that can be written down and shared. In their steadiness, sleep finds a kinship. Breath in, breath out. A chest rises and falls like a bellows. Around it, air slips and returns, weightless to the eye, weighted on the scale. A comfort once mysterious and now gently explained. Nothing grand is required to feel the shift. Take a glass of water and notice how bubbles form on a spoon when it is warmed and dipped. Watch a drop of vinegar meet a pinch of chalk and fizz with invisible conversation. Hold a hand near a kettle and sense how heat travels in a way your skin can count. These are friendly doors into the same house Boyle and Lavoisier arranged. Behind them, the atom waits with a patience worthy of stone, not to be worshipped, just to be used, as a neat way of saying what joins with what and how much of each, and why the world keeps its promise to behave. By the time their work settled into the bones of science, chemistry had slipped out of its old costume. Instruments replaced charms, equations replaced riddles. Air, once a whispering element, stood revealed as a mixture whose parts could be named, collected, weighed, and then given back to the sky. The four classical elements didn't die so much as retire with honors. Their long service remembered whenever a child points and says, fire or water. In their place, a quieter music took the stage. Proportions, conservation, Repeatability, the kind of rhythm that soothes the mind without dulling it. The door these workers opened did not swing shut. Others walked through carrying new lamps, asking about atoms and charges, about the warmth we call energy and the dances we call bonds. But the room itself, the one with the balance and the sealed glass, with the habit of measuring first and describing after, was already built. Step into it in imagination and feel how restful it is to live in a world that keeps track of itself. Pressure rises when space falls. Mass does not vanish when flames bloom. Air is not nothing. It is a crowd, honest and busy, pressing softly on your skin even as you rest, carrying sound when you need a voice, and falling silent when you draw the breath that carries you towards sleep. Under that same soft shine of brass and glass, a quieter courage took shape, pencils whispering over paper, numbers lining up like careful footprints, breath fogging the window by a small desk. In that gentle discipline, tomorrow's chemistry loosened its knots. Far from grand lecture halls out in the damp mornings and sooty evenings of industrial England, a modest school teacher named John Dalton kept faith with the invisible. He lived simply, spoke plainly, walked often, and counted everything he could: clouds, raindrops, how pressure leaned with the season. Chalk dust lived in his pockets. Patient rows of figures lived in his notebooks. He wasn't chasing spectacle. He was following steadiness, the same steadiness the new room of science had been built to encourage, and from that steadiness, the atom would begin to step into focus. Weather drew him in first. He loved how the sky could be measured, how a barometer's column rose and fell like a pulse you could read with your eyes. The air above towns and farm fields did not behave like a single ghostly essence. It acted like something that could be tallied, nudged, coaxed. The more he watched, the more the old question returned, softer this time, less like a shout and more like a hum. If different gases share a room, why don't they blur into one another perfectly? The way sugar melts into warm tea, why does each seem to keep some character of its own, as if composed of separate citizens who mingle but do not dissolve? Dalton let the question sit beside him like a quiet guest. He noted how nitrogen and oxygen, though neighbors in the same space, could remain stubbornly distinct in behavior. He weighed, he compared, he circled back. Somewhere, underneath the weather and underneath the glassware in laboratories across Europe, there had to be a simpler grammar. Perhaps the world was not a continuous fabric after all. Perhaps it was woven from countless small knots. He turned the idea until it clicked into a shape that could be used. Matter is made of tiny, separate pieces. Different materials are built from different kinds of those pieces. And when substances meet, they do not smear into one another without rules. They pair off in counts. He revived the old, nearly forgotten word and gave it working shoes. Atoms, not metaphors, but bookkeeping units with weight and habits. Hydrogen's atoms were not oxygens. Sulfurs were their own kind again. Reactions, he suggested, do not destroy these pieces, they rearrange them. If two elements combine, they do so in fixed whole number ratios, 1:1, 1:2, perhaps 1:3, but never half of a piece, no fractions of a building block. The world assembled like a toy set that clicks only at certain studs. He did something lovely and ordinary to carry people along. He drew pictures, little circles for atoms, symbols inside to tell one from another plane, for one element, marked for the next. Arranged in pairs and trios, they became the first simple portraits of molecules, childlike and brave. you could look and see why water is always water, a pattern of hydrogen and oxygen that always keeps to a faithful count. No matter how often you boil or freeze it, no matter how many rainstorms arrive and leave, the ratio does not drift. The idea had the kindness of arithmetic. 2 + 1 is 3. Water is itself. He gathered these thoughts into a book with a title that only a careful soul could love, A New System of Chemical Philosophy, and inside it placed a handful of postulates, straightforward enough to memorize by lamplight. All matter is made of indivisible atoms. Atoms of the same element share the same mass and character. Compounds are formed when different atoms join in fixed counts. Chemical change is not creation or annihilation of atoms, but their rearrangement. The heart of it was not a threat to wonder, it was a promise to order. Even when a flame leapt or a powder fizzed, the parts kept their number. Time would soften a few edges. Later generations would split atoms and discover isotopes, small differences in mass, hiding inside what once seemed identical. But the usefulness of Dalton's picture did not fade. It turned chemistry from a cabinet of curiosities into a room with labeled shelves. You could assign weights, write equations that matched what a balance would show, predict the proportions that must result before any flame was struck. His quiet was contagious. Other chemists weighed more tenderly, purified more carefully, compared more honestly. The lawfulness of combinations, the way certain elements meet only in certain counts, stopped feeling like a coincidence and began to feel like the way language itself works. Letters choose their neighbors. Sounds prefer their partners. Meaning grows from pattern. He did not need prestige to do it. He taught in a small Quaker school, walked the same streets of Manchester for years, and kept his weather journals to the end. His notes on color vision, later called Daltonism, came from the same intimate attention he gave to rain and air. He trusted what repeated. He trusted the scale. He trusted that if nature spoke in ratios, it must be because there were things to count that could not be split any smaller by chemistry's hands. The room grew larger because of him. A century's worth of bottles and powders began to line up not by smell or story, but by weight and behavior. And as the shelves settled, another voice entered, this time from the cold north, where winter wraps the city, and writers and scholars work within a brightness put there by snow. Dmitri Mendeleev sat at a table in St. Petersburg and did a stubborn, homely thing. He made cards. On each card he wrote the name of an element and what was known about it, mass as best they could measure at the time, density, how it reacted with others, the kind of oxides it formed, the ways it lit up or stayed quiet. Then he shuffled. He laid them out. He picked them up and began again. He did not begin with equations. He began with listening. Certain elements seemed like cousins, lithium, sodium, potassium, soft metals that greeted water with a quick, bright violence. Others, chlorine, bromine, iodine, shared a sharpness and smell and a hunger for electrons that would not be named so until later. When he arranged the cards strictly by the best masses available, some families fell out of step. He had a choice: worship the number or honor the pattern. He slid a few cards into positions that made the chemistry sing truer, even if their measured masses protested. Tellurium and iodine, for instance, he allowed to trade places on the page because their character demanded it. He trusted that if the world's song and the early numbers were out of tune, the numbers would later be corrected. Columns formed like trees in a careful garden. Each family kept its temperament as it climbed. Soft alkali metals on one side, noble gases still unknown as a complete set, waiting like a blank melody that would be filled in. halogens poised to complete other elements' stories, oxygen and sulfur sharing a rowdy steadiness. Across the rows, properties shifted with a rhythm you could hum. The shape was not a map of Earth or the sky. It was a map of possibility. What would react with what? Which compounds would likely form? Where softness would meet color? Where hardness would carry luster? The gentlest, bravest part was leaving spaces where a card should be, but no element had yet walked onto the stage. He left a gap and wrote a promise in the margins. "Something belongs here," he said. Not just something, a specific something with weight roughly so, with a density within this range, with an oxide of a given kind, with a melting character suited to this family. He named them provisionally, with a small flourish borrowed from Sanskrit eka, meaning one beyond. Eka aluminum would later step forward as gallium, a silvery trickster that melts in the hand, and matched his forecast like a letter sliding into an addressed envelope. Eka silicon arrived as germanium, carrying the same quiet satisfaction. Others came to fill the other seats. The table was not a chart so much as a calendar, appointments kept on time by nature. At first, the room was skeptical. As rooms go, arrangements had been tried before, and the precise weights then available were messy, but predictions give a model the right to stay. When the elements that Mendeleev had sketched in absence were found and measured, and their properties sat down exactly where he had set a place, the conversation changed. The periodic table was no longer a clever filing system. It was a view into order so deep that it could be followed ahead into the dark and still bring you home. His life sharpened that feeling of earned clarity. The boy from Siberia, the youngest of a very large brood, had seen factories fail and family fortunes evaporate. His mother, fierce and loving, carried him by carriage across long distances so he could study. That devotion lived in him as doggedness. He could be prickly, he could be grand, but under the beard and the winter coats was the same belief that guided Dalton. Nature is consistent. If you are patient and keep your notes, it will show you its repeats. He worked before protons had been counted, before electrons were drawn like glimmers at the edges of circles, before the atomic number was known as the true key to identity. He misread some masses not because he was careless, but because the tools of the time breathed and wavered. Yet the pattern, the periodic return of temperament as mass increased, was strong enough to overrule even official figures. He knew what family an element belonged to by the company it kept and the shapes of its bonds. When later instruments offered the clean integer of proton count, the old swaps he had made, like the brave exchange of iodine and tellurium, suddenly looked like foresight rather than error. The table had always been singing atomic number. It simply took a while for our ears to learn the tune. Between Dalton's dots and Mendeleev's grid, the world of matter became a place you could walk slowly through at night, touching door frames labeled with names you trust. Hydrogen greets you at the threshold, light and eager. Carbon offers 1,000 forms and the memory of wood smoke in winter. Iron stands with a kind of honest weight in the middle distance. The noble gases linger like polite guests who do not impose. Each has a seat. Each repeats in character with a regularity that feels like the planets returning to familiar parts of the sky. The gift of this order for a sleepy mind is simple. You can relax into it. When water forms from hydrogen and oxygen, it does so by counts the table whispers ahead of time. When salt crystallizes, the sodium and chlorine do not argue over ratios. They know the steps. When a piece of metal gains mass in the fire, as Lavoisier showed, the number is not a surprise to a chemist who can sketch the oxide and point to the column where oxygen lives. What once looked like whim, this powder turns blue. That one grows warm, became a choreography with marks on the floor to guide your feet. Imagine Dalton at his desk, drawing circles that stand for something he cannot see but can weigh in his way. Imagine Mendeleev leaning over a sea of cards, sliding one here, another there, until the repetitions click and the gaps feel less like absence and more like patience. They are not conjurers. They are neighbors who label the drawers and keep track of the keys. Their craft is not to dazzle, but to make the world's working parts findable in the dark. In that kindness, chemistry grew calm. Instead of powders with personalities described in prose, there were elements with places and numbers. Instead of recipes guarded by the pride of a single workshop, there were equations that any student could balance with paper and care. The laboratory kept its smells, its heat, its small triumphs when a crystal forms cleanly or a color blooms exactly where expected. But beneath the color lay a grid, beneath the flame a count, beneath the count, the quiet insistence that matter, in all its variety, is made from pieces that know what they like. As newer instruments pried deeper electrons traced into shells, nuclei weighed, charges counted, the table only grew clearer, not smaller. The columns proved to be families for reasons stronger than resemblance alone, and yet the feeling in those old portraits still holds. Dalton's circles look childlike because they honor a child's good sense. Draw what you can carry in your head, then test it. Mendeleev's blank spaces feel tender because they honor the future. Leave room for what you don't yet know, and set a clean place for it to sit when it arrives. If you listen closely now, in the quiet of your room, you can hear their work like a soft refrain. You don't need to see the smallest pieces to befriend them. You can weigh a breath, count the ratios, lay out the cards, and let the pattern teach you how it wants to be read. Trust that water stays itself because its parts meet faithfully, that iron takes on a certain color and weight in flame because oxygen is a steady partner, that gaps in understanding are not failures, but invitations. The table on the wall isn't a chart of riddles, it's a lullaby of order. In that lullaby, atoms stop being rumor and become a language you can think in, a soft grammar for the solid world, a way to name what holds while you breathe. Turn to a comfortable side and let the mind drift, content that even in the dark, everything is quietly counting itself. And then the missing lyric found its note. The true key was not a heavier number, but a simpler one. Atomic number, how many positive charges rest in an atom's heart, quietly explained why the table's pattern holds so gracefully. Mass had been a kind guide, close enough to sketch the melody, but it was the count of protons that fixed each element's pitch. In a pleasing twist, Mendeleev's intuition had already seated most cards where they belonged. He trusted the song more than the shaky scales of his day. And the song, in time, proved him right. He was never just the keeper of a grid. He wandered far, oil refining, fertilizers and harvests, even the standard by which vodka should be measured and sold, so that quality wouldn't drift with rumor or mood. He once reached for a grand unifying story, to cradle all of nature at once. That ambition didn't land, but the reaching itself was faithful to his temperament. Whether he handled molecules or markets, he wanted order that served people a logic that could be used. The table he left us has grown longer, grander, a little stranger around the edges, yet the bones are the same. New elements step onto the stage. New rows unfold like careful steps in a dance. Students trace the pattern with a finger and feel the hush of recognition. Here is a map that has not blown away in the wind. It is more than a reference. It is a small emblem of how the universe repeats itself with kindness. There is comfort in the thought that nature keeps time. The elements, those raw notes from which stars, stones, and soup are composed, line up and return in regular intervals like a lullaby. Mendeleev did not just give us facts to memorize. He gave us a picture to rest the mind upon. Families gathered by likeness, differences that change in a rhythm you can learn to hear. It began with cards on a desk, a stack of notes, and a refusal to accept that the world could be only a drawer of mixed spoons. By the end of the 19th century, atoms felt settled, solid, indivisible, politely dependable. Dalton had given them weight and character. Mendeleev had filed them into an orderly cabinet. It was a tidy story, the kind that lets the mind drift contentedly toward sleep. And then, a small green light flickered in glass and refused to obey. Vacuum tubes, slender vessels with most of their air coaxed away, were scattered across laboratories like captured fireflies. When a high voltage nudged two metal electrodes into conversation, a ghostly glow leapt from the negative end. A beam traced an invisible path through the emptied space. Fluorescent coatings on the glass woke where the beam struck. Tiny paddle wheels set in its path began to turn. These cathode rays were not ordinary light. They cast crisp shadows. They pushed things. They carried momentum like messengers with weight. What were they? Waves, said some exquisite vibrations inside the glass. Particles, said others, but particles of what? Atoms were supposed to be the end of the road, the smallest coins in nature's purse. What smaller coin could be spent from them? A gentle, precise mind in Cambridge set about bending the mystery into an answer. J. Thomson did not announce himself with thunder. He adjusted dials, balanced fields of electricity and magnetism, and watched how the beam curved when those fields were tuned just so. If the rays were made of charged particles, the curves would tell their secret, how much charge each carried compared to how much mass. The curves spoke clearly. Whatever was flying across that tube was unimaginably light, thousands of times lighter than hydrogen, and carried a negative charge. It was not an atom, it was a part of one. The atom, which for 2,000 years had been a final word, suddenly had syllables. Thomson had given the first of them a name, the electron. A new world opened beneath the old. The picture of the atom had to change shape to hold this new guest. If atoms as a whole were neutral and yet contained negatively charged electrons, there must be balancing positive charge somewhere inside. Thomson proposed a model that borrowed its shape from dessert, a softly positive sphere with little raisins of negative charge dotted throughout. People smiled at the name plum pudding, fruit and custard, but the image had a practical calm to it. The charge balanced, the atom stayed whole, the new particle had a home. For a time, this worked the way a first sketch often does. It explained neutrality. It invited chemists to imagine electrons embedded in matter, free to shift positions when bonds formed and broke. It said, gently, that the atom had inner structure without asking anyone to jump too far at once. But atoms have a way of confessing under the right questions, and another voice, warm and booming from far across the world, was about to ask one with a bit of mischief in it. Ernest Rutherford was fond of boldness that still felt clean. He had already listened closely to the quiet decay of radioactive elements and learned to distinguish the kinds of particles they emitted. Now he wanted to aim those particles with intention and let matter answer. He chose alpha particles, positively charged and comparatively hefty, small cannonballs in a microscopic war, and he set them against a sheet of gold so thin it might as well have been sunlight pressed flat. The expectation was ordinary. If atoms were diffuse puddings of positive charge, the alpha particles would sail through with only the softest nudges, like peas drifting through fog. With Hans Geiger and the young Ernest Marsden, Rutherford posted a watch in the dark. They counted little flashes on a screen as each particle arrived. Most of the flashes landed where expected, straight on, a slight drift, a small angle here or there. Then came a few that behaved like impossible jokes, large swerves, wild ricochets, and, now and then, a full reversal back toward the source, as if a cannonball had struck tissue paper and bounced. Rutherford laughed, and later he would say it felt as unlikely as firing at a piece of soft curtain and having the shell return. Glee aside, the result was stern. Something inside the atom was not fog and not pudding. It was small, dense, and strong enough to turn an alpha particle around. The only sensible model was a dramatic one. Almost all of the atom's mass and all of its positive charge must be gathered into a tiny central knot. Call it a nucleus. Around it, the electrons must dwell, held by the attraction between opposite charges. The scale of the emptiness between is humbling. If the nucleus of a hydrogen atom were the size of a marble, the most likely place to meet its electron would be nearly a football field away. The atom is almost entirely room, an airy hall with a pebble at its center, yet it behaves with a solidity we trust. Tables hold cups, floors hold footsteps. The heart is small, the influence vast. This nuclear model swept the old pudding away and gave a sturdier reason for Rutherford's scattering. Alpha particles skimming close to the concentrated positive center would be pushed aside at sharp angles. Those that came very close would be flung back. Most saw nothing dense in their path and went right through, a graceful nod to the emptiness inside all matter. Suddenly, chemical behavior had a new anchor. Here was a core to give weight and charge. Here were electrons to negotiate bonds at the edges. Questions flowered naturally. If electrons circle a nucleus the way planets circle a sun, why don't they radiate away their energy and fall in? Classical physics said an accelerating charge should lose energy as light and spiral inward. If that were all, atoms would collapse in the wink of a nightlight, and the world would run like water through a sieve. Yet faces and teacups stay whole. The puzzle sat politely in the corner, inviting a new kind of thinking that would soon arrive with its own soft strangeness. For now, it was enough to feel the shape of the room, a dense center, delicate outskirts, space between where imagination could breathe. Rutherford's own path did not end at the nucleus. He weighed its charge by watching how many particles turned and by how much. He inferred that the number of positive charges must match the place of the element in the periodic pattern, the same counting that atomic number later made precise. He glimpsed yet another resident of the nucleus without naming it outright, sensing that positive charges alone were not the whole recipe. A neutral partner would be identified in time. The stage was set. The actors were taking their marks. Meanwhile, Thomson continued to trace the family of particles he had helped reveal. He separated charged fragments from gases, sorted them by how their paths bent in fields, and built the first tools that would become mass spectrometers, the quiet machines that weigh invisible things. He studied ions, tasted the difference between one isotope and another long before the word was common, and showed that even within a single element, atoms could carry slightly different hefts. The indivisible had become articulate. Beneath the changes, notice how the mood of science stayed kind. Tools were humble, glass bulbs, hand-cut foils, chalk marks in dark rooms. The claims, when they came, were modest and firm. A beam bends this much in that field. A particle turns here and not there. Most pass through, a few return. From these small, repeated facts, the world's inner design drew itself like frost on a window, branching, then repeating, then settling into a figure you could trace with a fingertip. If you stand quietly inside this story, its comforts return. The periodic table holds because identity is counted in the nucleus, not guessed by weight alone. Electrons exist because the beam that should have been light turned out to be a river of charged specks. Atoms have cores because cannonballs sometimes bounce from curtains. The metaphors are soft, but the numbers are not. A pattern strong enough to predict new elements is strong enough to forgive early errors and keep its promise anyway. A model generous enough to be replaced by a better one is generous enough to teach along the way. What you can carry into sleep is simple. The smallest world is not chaos. It is spacious and precise. Charges balance, masses gather, paths curve for reasons you can learn to expect. Between the marble and the stadium, between the nucleus and the electron's long reach, there is room for everything you love: paper, wood, water, skin, to be both airy and steadfast. And all of it began, for us, with a flicker in a glass tube, a green light that would not behave, the soft click of cards on a table, a few bright dots on a screen in the dark. The atom was not the end of the inward road. It was a door. Behind it, more rooms waited. But already, by the time Rutherford's marbles met Mendeleev's families and Dalton's circles, the house felt wonderfully livable. Neat shelves, strong beams, broad halls of empty space where the mind can walk at night and not bump into anything it does not expect. Let the thought rest here. Nature leaves clues that a patient hand can gather. It lets pattern outweigh pride. It lets a table sing the right tune for a century and a half. It lets a beam show you its curve, a foil show you its heart, a scattered flash tell you that underneath polish and shine there is a kernel holding fast. The universe, for all its distances, is neighborly at small scales. It tells you what it likes, and it keeps its word. And then, almost shyly, the proof arrived. They used almost nothing, just a small source shedding alpha particles like quiet embers, a leaf of hammered gold so thin it trembled at a breath, and a dark room where a faint screen blinked whenever a particle arrived. Patience did the heavy lifting. Someone leveled the apparatus. Someone checked the angles twice. Someone counted tiny sparks until numbers became a language. Out of that simplicity, a hidden architecture spoke. No great engines thrummed. No computers solved while anyone slept. Only hands steady enough to hold the question still, and a mind willing to let surprise become a teacher. Ernest Rutherford had a gift for turning astonishment into clarity. He liked jokes. He liked noise, but he loved plain thinking most of all. When a student wrapped themselves in unnecessary algebra and sighed that the problem couldn't be done, he was known to stiffen gently and remind them that can't is a word reserved for what nature forbids, not for what we simply haven't tried properly yet. That mix of humor and steel suited a person who listened for truth in small flashes. He and his colleagues, Hans Geiger, careful as a metronome, and the young Ernest Marsden, tireless and game, let alpha particles whisper the atom's secret by bouncing them, one by one, off a sheet of gold. He did not stop at the bounce. As the years turned, his curiosity stepped over the threshold he had opened. He watched how nuclei could change character, how one element could become another, not by alchemy's dreams, but by transformations in the heart of the atom. The lesson was bracing and tender at once. Identities that had seemed everlasting could shift when the nucleus rearranged itself, and yet the rules were faithful enough to learn. From this patience, a new field stood up, brushed off the dust, and went to work. Nuclear physics learned its first words in that room: the grammar of reactions, the scale of energies, the hint that new particles waited in the wings. What changed wasn't only a diagram in a book, it was the way the mind pictured matter. The atom refused to stay a tidy, indivisible bead. It became a small chambered house, a dense core holding nearly all the weight, electrons living far away by comparison, most of the volume, a clear stillness stretched between them. The world we touch, wood, skin, steel, turned out to be mostly emptiness, bound together by quiet force. There is a soft irony in that. Push your palm to a table and feel its firmness. Then remember that what greets you is the electric insistence of particles keeping respectful distance. The more closely you look, the more absence you meet. The more absence you meet, the more you understand the power of what remains. Rutherford's picture would be tuned, not overturned. Others would explain the electron's motion in new terms, would name the forces that stitch the nucleus together, would write rules that seemed to grin at our older instincts, and then keep their promise anyway. But the center holds. Atoms have a concentrated heart and airy outskirts. That insight arrived on the day a few alpha particles turned around and came home again, refusing to pass through as fog. A simple setup, a few specks, a screen that flickered, and a question asked without pride: why did that one bounce? Time, as it likes to do, added another riddle. By the early 1930 seconds, the nucleus looked a little crowded. Positively charged protons, packed close, somehow content, like charges repel. Every school child with a pair of magnets can feel it. So how did these neighbors sit so near without flying apart? And if you added up a nucleus's mass with the pieces you thought you knew, protons here, electrons out there, the numbers limped. There was always a bit of extra weight, a quiet surplus that refused to explain itself. Something had to be living in the nucleus, something that could lend heft without adding electric shove or pull. James Chadwick entered with the kind of presence that murmurs rather than declares. He did not look like thunder, but he listened like rain. He returned to an experiment that had left people puzzled. When beryllium was struck by alpha particles, it emitted a strange, penetrating radiation. Many assumed it was an especially fierce kind of light, gamma rays, but the energy looked wrong, too forceful to be an ordinary beam. Chadwick tried a different angle. What if this wasn't light at all? What if it was a stream of neutral projectiles flying so cleanly that electric fields could not catch them? He let that mysterious radiation strike simple targets, hydrogen-rich materials, nitrogen, and watched how those targets recoiled. The recoils were not the shrug of light on matter. They were the jolts of collisions between things with similar mass. From the angles and the speeds, a neat answer emerged. The beam was made of particles about as heavy as protons, but with no charge. He had found the neutron, the quiet sibling at the center of the atom. It wasn't theatrical, no green glow, no clatter of paddle wheels, just a shift from something to someone, and yet that modest presence did heroic work. The neutron filled the mass ledger so the numbers finally balanced. It explained why atoms of the same element could weigh slightly differently while behaving the same in chemistry. Isotopes are families distinguished by neutrons. Carbon with 6 protons and 6 neutrons is carbon 1,2. Tuck in one more neutron and you have carbon 1,3. Tuck in 2 and you have carbon 1,4, which whispers time by slowly changing, letting archaeologists and geologists count backward through centuries. The neutron did more. It made peace in the crowded nucleus. Protons push each other away because of their like charge, but neutrons neither push nor pull electrically. They bring mass, and through a deeper bond, the strong nuclear force help knit the nucleus together. That force, short-ranged and fierce, overwhelms the electric quarrel when particles huddle close enough. Think of the neutron as a patient middle child at the table, hands out, steadying the meal so it isn't tipped by sibling energy. Without it, the heart of matter would be a nervous place. Because they carry no charge, neutrons slip into nuclei, with a grace denied to protons and electrons. That grace became a key. Aim slow neutrons at heavy atoms, and something dramatic can happen. The nucleus accepts the visitor, wobbles, then breaks apart into pieces that fly with energy, tossing out more neutrons as they go. A chain begins, one event begets the next, until the room is bright with possibility and danger. From that chain came 2 roads we still walk with care: the harnessed heat of nuclear power and weapons that haunt the world's sleep. The neutron does not ask for spotlight, but stage lights moved to follow it anyway. Chadwick received a medal shaped like gratitude and took his quiet back to work. He understood the double edge of what he had helped reveal. In wartime, he joined projects that bent nuclear knowledge toward urgency. In peacetime, he kept the tone even and the claims careful. Meanwhile, the neutron showed off elsewhere in nature. In the pressed hearts of exploded stars, matter is squeezed until protons and electrons marry into seas of neutrons, forming objects so dense a spoonful would outweigh a mountain. At cosmic scales and in careful laboratories alike, the same uncharged actor keeps the plot moving. By then, the atom's portrait felt complete enough to hang. Electrons out in the rooms where chemistry happens, a nucleus inside bearing protons and neutrons, the family finally named. Yet, even as the picture settled, another mystery asked for a seat, a mystery with a familiar face, the one that wakes you in the morning and paints the pages you read at night. Light, which had always felt friendly and simple, would not stop misbehaving under close attention. For a long while, the wave story felt sufficient. Thanks to Maxwell's equations, light made sense as an electromagnetic wave, a ripple that travels without needing a medium, a rhythm with wavelength and frequency, a song that reflects, refracts, and diffracts with grace. Waves were continuous, smooth, reassuring. Then came the places where the smoothness broke. An old problem glowed hot in the corners of physics: blackbody radiation. Idealized objects that absorb all light and re-emit it in a characteristic spectrum were supposed, under classical rules, to spray infinite energy at the highest frequencies. The math insisted on a catastrophe that the world refused to deliver. Max Planck, cautious and loyal to the old ways, wanted only to fix the numbers. In what he later described as a desperate step, he suggested that energy isn't paid out in a steady stream, but in quanta little bundles whose size is set by a new constant, h. In his formula, the energy of one bundle is h times the light's frequency. Higher frequency, bigger bundle. Suddenly the curve matched the lab. The catastrophe evaporated. The room exhaled. Planck did not announce a revolution. He left the ontological question politely on the coat rack. Were quanta real, or just a clever accounting trick? A clerk in a patent office, Careful, imaginative, fond of trains and clear clocks, took the next stride. Albert Einstein treated the quanta as real and let them explain something stubborn, the photoelectric effect. Shine light on certain metals and electrons are ejected. Under the wave picture alone, brighter light should eventually knock electrons free, regardless of color, but experiments said otherwise. Low-frequency light, no matter how intense, could not liberate the electrons. High-frequency light, even when dim, did so immediately. Einstein's answer was simple and bracing. Light comes as packets, photons, each carrying energy proportional to its frequency. A photon below a certain threshold simply cannot pay the price to free an electron, no matter how many arrive. Above the threshold, even a few will do. Brightness counts how many, color counts how much. The explanation was so clean it looked inevitable in retrospect. For it, he received the prize that marks a good idea as a lasting one. The world learned a new shyness then. It had to admit that both pictures could be true in their ways. Light behaves like a wave when waves serve the question. It behaves like a particle when particles answer better. Energy is not a syrup. It arrives in drops. The universe is not a smooth sheet. Under your fingertip, it has a grain. This was not an invitation to chaos, but a request to accept that nature's language is bilingual. The mind could loosen and let both dialects live. Back at the nucleus, the bilingual lesson continued. Protons and neutrons began to look like composites when probed with higher energies, quarks inside, held by a force that behaves politely at large distances and fiercely at short ones. But that is another path down, and not ours tonight. Our thread is gentler. Rutherford's screen, blinking like a far constellation in a small room. Chadwick's targets, jumping almost imperceptibly. Planck's constant, taking its place among the numbers the world cannot do without. Einstein's photons turning a metal plate into a small stage where light proves itself one particle at a time. What comforts here is not only the answers, but the posture. The experiments are spare, the claims are clear, a thin foil, and the world admits a nucleus. A beryllium target and a neutral traveler steps into view, a dim lamp on a metal surface, and light reveals its granularity. You do not need to force the universe to sing. You quiet the room, you place the apparatus gently, you ask a question that can be repeated, and you listen for the same note tomorrow. Walk through these rooms once more before sleep takes you. First, the gold foil, where most alpha particles pass like whispers and a few return like small, polite shouts, reminding you that even in emptiness, there is a heart. Then the laboratory with its battered sources and patient notebooks, where a neutral particle makes the arithmetic honest and holds the siblings together at dinner. Then the black body curve, once threatening to blow to infinity, now sitting smoothly under a constant's care. Then the metal plate where dim violet light looses electrons with ease, while brilliant red fails with dignity, proving that brightness isn't everything, that sometimes it's the pitch that matters, not the volume. All of it together leaves a feeling like a warm hand on your shoulder. The smallest world is delicate without being fragile. It is built from parts that keep their promises, even as they surprise you with new ones. Forces push and hold, charges balance, energy arrives in measured steps, and in the wide space between nucleus and electron, so much room you could almost hear it breathe. The invisible patterns that hold your cup, your book, your heartbeat, and your rest stay steady. Let that steadiness be a pillow. Let the questions you still carry settle like dust in a sunbeam. The screen will keep blinking, the numbers will keep matching. The laws will keep making room for grace. And light, with its shy double nature, will keep crossing the room to find you, as dependable as morning and as strange as the first star you ever saw. Shine a beam through two narrow openings, and the wall beyond answers with a quiet zebra of light and shadow. Waves do this crest meeting trough to cancel, crest joining crest to glow brighter. That part is familiar. What slipped the mind's net was what happened when the light was dimmed to a hush and allowed through one photon at a time. No crowds, no overlapping ripples from different particles, just solitary travelers, separated by long pauses, tapping the screen, one pinprick at a time. Wait long enough, and the same delicate pattern appears. It is as if each photon has taken both paths, argued with itself in the dark, and decided where not to land. That is the first soft shock. The smallest actors carry more than one story at once. The language for this became wave-particle duality, a phrase that sounds like a truce. It says, stop asking which one light really is. Ask instead how you questioned it. Shape your experiment like a wave test, and light sings as a wave. Shape it like a particle test, and light clicks like a bead on a counter. The decision is not made in a boardroom behind reality. It's baked into the way you touch it. Even more disconcerting, the same behavior appears when you swap photons for electrons or for whole atoms. The pattern is stubborn. The universe, at its smallest scales, does not like to be pinned to a single costume. Certainty gives way to likelihoods, not because the tools are sloppy or the hands are tired, but because the world itself, under close attention, prefers probability. A particle's future is a fan of possibilities. Its presence is a mist of where it might be until an interaction narrows the choices. That narrowing is not a moral drama. It's just how information behaves when matter and measurement keep each other company. The old clockwork image gears interlocking, every motion predictable if you start the stopwatch, exactly keeps working for planets and pendulums. In the domain of the small, the clock hums jazz. Meanwhile, light carries another surprise with a steadier face. In a vacuum, it always moves at the same speed. A fixed heartbeat that does not change just because you are running or resting. To keep that pace sacred, space and time adjust themselves. Lengths contract, durations stretch, simultaneity slips. It is a beautiful oddity. The more you insist on hurrying, the more the universe adjusts the flooring beneath your steps so that the lamp's glow still outruns you at the same measure. Light becomes a kind of metronome for cause and effect, keeping order in a way that bends intuition without breaking it. These insights did not arrive as thunderclaps. They came as glimmers, glowing filaments, polished plates that released electrons under illumination, faint colors coaxed from heated salts. A handful of numbers refused to fit inside classical walls, and instead of forcing the numbers out, physicists rebuilt the room. That room came to be called quantum theory, and it offered not merely new facts, but a new grammar. Energy arrives in steps, not syrup. Measurement participates. It does not simply witness. Position and motion, when pursued with zeal, trade precision like two friends sharing a single coat in winter. The atom stood in the middle of this rearrangement, half familiar and half mirage. Electrons existed. A nucleus carried nearly all the weight. Rutherford had shown there was more emptiness than substance in between. Yet the picture was contradictory under old arithmetic. If an electron were a tiny bead circling a nucleus the way a moon circles a planet, it would be accelerating, changing direction continuously, and an accelerating charge should radiate energy, slow down, and fall inward. By that argument, atoms should collapse. They did not. Teacups held, breath warmed, stars shone. Something in our description needed mending. A tall, gentle Dane, with a taste for paradox, took a careful needle to that seam. Niels Bohr loved clean ideas and accepted that sometimes clarity arrives with odd edges. He noticed something the world had been humming for years. When you excite a gas hydrogen, say it does not glow with a continuous rainbow, but with knife-thin lines at particular colors. Line by line, like notes on a scale. Each element owns a pattern, a signature. Chemists used those signatures as labels. Astronomers read them across gulfs of darkness to learn what stars are made of. But the why of the pattern, the instrument playing it, remained unnamed. Bohr proposed that electrons are choosier than our old picture allowed. They do not occupy every possible distance from the nucleus. They live on rungs, specific energy levels, where they can rest without bleeding light. Between rungs, no stays. A jump upward requires a precise gift of energy. A drop downward returns that exact gift, a photon, with a frequency equal to the gap. Electrons, in this view, are not little moons so much as acrobats moving between perches, releasing a flash each time they land, with a thump on a lower bar. Hydrogen spectral lines became arithmetic. Each color belongs to a particular fall. When Bohr wrote the numbers down, the results matched what laboratories had been seeing with prisms and plates. Prediction replaced shrug. The barcode of hydrogen could be computed rather than merely admired. The model wore classical clothes, tiny worlds circling a sun, but its spine was quantum. Energy came in packets, orbits were quantized. The atom had a rhythm with rests and measures. It was a bridge, sturdy enough to walk across, flexible enough to sway with the wind of new facts. Bridges do not end journeys. They let you reach the next shore. Bohr's picture struggled as atoms grew crowded with more electrons. It could not explain every color in more complex spectra, nor could it fully justify why electrons in allowed orbits did not radiate away their energy. But it gave the imagination a handle while the mathematics grew up behind it. It taught a generation to hear quantized notes before showing them the whole orchestra. Another voice, younger and sharp as winter, arrived to tidy the language itself. Werner Heisenberg preferred equations that talked to the data over metaphors that talked to the soul. He turned his attention to the two questions that earlier ages assumed could be answered together. Where is the particle? And how fast and in what direction is it moving? For billiard balls or planets, there is no quarrel. Measure carefully enough and you can know both to any precision you like. Heisenberg's calculations said the microscopic world refuses that bargain. The tighter you pin down position, the more momentum slips away into fog. Pin down momentum, and position spreads into a cloud. The product of those uncertainties cannot be squeezed below a certain small amount, a limit set by the same constant that quantized light's energy. This is not a confession of clumsy tools. It is the fabric's weave. Try to see the electron with very short wavelength light to get a crisp position, and the photon you use kicks the electron hard, scrambling its momentum. Use a gentler, long wavelength light to disturb the momentum less, and your view of position blurs. The trade-off is not a nuisance. It is the price of admission. You are not peeking at a pre-written script. You and the system are writing together, line by cautious line. Heisenberg's uncertainty principle did more than redraw the lab's boundaries. It taught a humbling posture. Ask what can be known at once, and plan your questions accordingly. Replace the picture of a particle tracing a thin wire with a map of likelihoods, a cloud that says, "Here is where you are most likely to meet it." The electron becomes not a marble, but a mood. It is not nowhere. It is smeared in a calculable way, and the smear itself holds the rules for how it will respond when called. Some found this intolerable. A certain patent office romantic who had taught us how light bends time bristled at the dice on the table. He was not alone. We do not like giving up the right to imagine that the world carries full details behind a curtain, waiting for us to pull it aside. And yet, experiment after experiment refused to honor that preference. What worked was a quieter faith, that probabilities obey strict arithmetic, that ensembles of events are law-abiding, even when each particular outcome looks like a coin toss, and that the sums we write for these clouds and quanta will keep agreeing with what the screens show. The dual nature of light, the way it draws interference patterns and then taps detectors one photon at a time, was mirrored by the matter we thought was unquestionably particle-like. Electrons formed interference fringes in double-slit tests. Neutrons, and even whole atoms, could be coaxed into similar games. The line between wave and particle stopped being a fence and became a threshold you cross depending on how you walk. Ask for phase and you get interference. Ask for which path and you get clicks. Ask for both at once, and the universe smiles sadly and says, gently, that you cannot. These ideas did not make the world colder, they made it precise. Spectral lines are not just pretty, they are the signatures by which we read the composition of distant suns and the motions of swirling gas. The quantized levels in atoms explain why matter is stable, why chemistry has the shapes it does, why bonds form in the angles they prefer. Uncertainty explains why electrons do not collapse into the nucleus. Their wave-like nature provides a pressure that keeps atoms from shrinking to nothing. Light's packets explain why a dim violet can do what a bright red cannot, freeing electrons from metals and setting spark to silicon. As the mathematics matured, the atom's portrait changed again from Bohr's tidy orbits to orbitals, those silent cloud shapes that say where an electron is likely to be found. Spheres and dumbbells, toruses and petals, a garden of probability arranged around a nucleus like rooms around a hearth. No little planets now, but a family of shapes that tell chemists which directions bonds will reach, which materials will conduct, which crystals will shimmer. The pictures look like art because nature's economy often arrives wearing beauty. Through it all, light kept its double life. It diffracted around edges and arrived in packets. It refused to let anyone keep both path information and interference at once. It moved at a speed that would not flex, asking space and time, instead, to do the bending. It carried the energy of electrons, changing their minds, and the information we use to move words and music across oceans. It is a patient teacher that rarely raises its voice. Stand in a classroom for a moment in your mind. A hand draws Bohr's atom circles and dots, while the teacher acknowledges the limits of the sketch. The picture is wrong if you stare at it too long. It is right enough to begin. A prism waits near the window. A lamp and a tube of hydrogen are ready on the bench. Flip the switch, and there it is. A few clean lines on a dark background. A pattern that could be mistaken for simple decoration if you didn't know it was the atom singing. You could spend a lifetime translating that song into the shapes of molecules and the colors of stars. The strangeness never stops entirely. it becomes a friend. It offers you uncertainty not as a threat, but as a way to loosen the grip of false precision. It offers you duality, not as confusion, but as a reminder that questions have tone as well as content. It offers you quantization, not as a jagged staircase, but as a rhythm. It offers you the double slit as a bedtime story about humility. Even when you ask the universe to go through one doorway at a time, it reserves the right to use both. Think about the tools that made this language. Slits sliced in metal with the care of a watchmaker. Filaments warmed until they glowed. Plates coated to blink at single photons. Electromagnets tuned until a beam bent just so. Spectroscopes turning light into a ledger of lines. None of these are palaces. They are musical instruments in modest rooms. They remind us that at small scales, the questions worth asking are often the ones that fit on a tabletop and can be repeated tomorrow without fanfare. As the century turned and turned again, new voices joined Schrödinger, writing waves and equations, Dirac marrying quantum rules to relativity's stern grace, Born giving probability a formal home, Pauli laying a simple prohibition across electrons so they wouldn't pile into the same seat. Each name added a plank to the bridge Bohr began. Each plank came from listening hard to what light and matter were already saying, not from forcing them to adopt a neater accent. When you look back from here, the milestones line up with a calm inevitability. The slit pattern that forms one dot at a time. The hydrogen lines that fall exactly where a simple formula says they must. The impossibility of pinning down both position and momentum without paying in uncertainty. The inviolate speed of light tearing and mending our notions of time. The electron that is sometimes a wave and sometimes a particle, and always something slightly beyond either word. The path was not straight, but it is walkable, and the view from it is gentle enough for the night. Let the mind drift a little over these images. A photon hesitates across two doors. An electron considers a cloud of places and chooses one when asked. A spectrum blooms from a thin glass tube, each line a testimony to an electron's fall. A chalkboard carries a short inequality that sets a floor beneath our curiosity, saying only, "This much fuzz is forever." A prism splits a ray into a fan. A detector clicks. A student smiles at the shock of something so tiny leaving such a confident mark. What is left is not confusion, it is poise. You are allowed to live in a world where some questions do not have single, sharp answers, and yet all the answers you can obtain add up. You are allowed to treat light as both spread and dot, to treat electrons as both mood and grain, to plan experiments that whisper rather than shout. You are allowed to keep two pictures in your pocket and know which to pull out by the light in the room. The smallest world does not promise simplicity. It promises coherence. The interference fringes keep their spacing. The spectral lines keep their places. The uncertainty refuses to shrink below a set threshold. The speed of light remains the same heartbeat in every empty room. These are soft rails you can hold while you fall asleep. The universe is not a broken clock. It is a living score. Sometimes it plays a wave. Sometimes it taps a particle. Always it keeps time. And once you learn to hear it, even the hush between notes feels friendly, like the quiet space between stars that lets constellations exist at all. The person doing the looking became part of the thing being looked at. The border blurred, and a gentler kind of physics stepped forward. Instead of hard marbles zipping along fixed tracks, we began to speak in wave functions, soft maps that describe possibilities rather than certainties. An electron wasn't tucked neatly here or there. It was most likely in one region, less likely in another, and vanishingly unlikely elsewhere. Only when you touched the system with a measurement, when you asked a very specific question, did that fan of possibilities narrow to one answer. The wave function did not so much shatter as fold, settling into a single outcome among many that were allowed. It's a little like placing a coin beneath a cup and refusing to peek before you lift the cup. Heads and tails aren't decisions made elsewhere, waiting to be reported. In the quantum mood, the coin is suspended in a poised maybe, a superposition. Lift the cup, perform the measurement, and the maybe resolves. Not both, not neither. Something stranger that carries both possibilities until the question is asked cleanly enough to deserve an answer. This tenderness is not limited to electrons. Heisenberg's uncertainty principle, set down with care and a small, beautiful constant, reaches across scales. In principle, it governs you, me, a coffee cup, a sock, drying on a line, everything, because it is not a flaw in our instruments, but a texture in the world. For large objects, those uncertainties are so tiny that life can ignore them. A baseball has a position and a speed you can know to absurd precision for all practical purposes. But at the size of electrons and photons, the uncertainties rise from a whisper to a voice. There, the trade-off is unavoidable. Sharpen your knowledge of where, and the how fast blurs. Sharpen the how fast, and the where smears into a cloud. The old clockwork did not break. It lifted its lid to reveal a second mechanism, running in parallel with its own rules. The payoff was astonishingly practical. From this probabilistic picture, this willingness to write equations about likelihood rather than certainty, came transistors and semiconductors, the diodes that make radios sing, the lasers that read music and knit tissue, the superconductors that carry current without complaint when they are cooled into stillness. Even the promise of quantum computing grows out of this willingness to let a system hold many states at once, and to choreograph those maybes into an algorithm. And when we whisper secrets across fiber and air, quantum rules offer new forms of protection. Eavesdropping changes what is being transmitted, and the disturbance itself becomes a warning. Humility sits at the center like a small lantern. The principle does not say, "You will do better if you try harder." It says, "You have found the floor." Nature is kind in telling you where certainty ends. The lesson is not to despair, but to ask better questions, questions that fit the scale of what is being measured. Probability becomes companionship, not defeat. The world's foundation is not a rigid grid. It is a woven fabric that flexes, and from that flexing, structure emerges. Atoms keep their shapes. Molecules keep their angles and preferences. Stars burn with dependable light. Order rises from a base that is fundamentally uncertain, the way a melody rises from notes that, taken alone, are only options until a player chooses. The atom, seen this way, is less a machine and more a living pattern. Not alive like an animal, but alive like weather, dynamic, lawful, beautifully behaved, and yet never exactly the same twice under a microscope of infinite precision. Once you accept that posture, your tools and your language lighten. You stop pushing for an answer the world does not offer, and instead learn to read the map of likely outcomes, the gradients that tell you where the path prefers to run. Into this map stepped a quiet, powerful equation and a thinker with a taste for clarity. Erwin Schrödinger gave the wave function a home to live in and a law to follow through time. His equation is simple to write, stern to solve, and generous in what it returns. As Newton's laws describe how positions and velocities change for billiard balls and planets, The Schrödinger equation describes how the wave function itself evolves, how a quantum state spreads, interferes with itself, and reshapes under gentle or jagged forces. The wave function is not a ripple you could surf or a shimmer you could film. It is a careful recipe for prediction. Fold into it everything that can be known about a system at once. Position-like information, momentum-like information, energy, spin, and you get a single mathematical object whose squared magnitude gives a probability distribution. Shade that distribution on an invisible canvas, and you have a heat map of where a particle is likely to be found when you finally ask, "Where are you?" The strangeness is not that we lack details. The strangeness is that before we ask, the details do not exist in the way classical language wants them to. Schrödinger was not content with symbols alone. He wanted pictures a mind could carry. Inspired by de Broglie's suggestion that matter has wave-like character, he built a wave equation for electrons bound to a nucleus. Out of that equation poured numbers that matched the energy levels measured in hydrogen, and then shapes the orbitals that chemists would come to know by heart. The tidy circles of Bohr gave way to clouds, spheres for s orbitals, dumbbells for p, clovers for d, elegant knots for f. These are not tracks. They are zones of likelihood, the soft geometry of where an electron prefers to be found. The math worked so well that it invited a philosophical ache. If the wave function contains every possible truth about a system, and if it evolves smoothly and predictably until a measurement is performed, then what, exactly, is a measurement? Is it a physical interaction like any other, or a special event that causes a sudden collapse from spread out, maybe to a single fact? Extend that unease from atoms to everyday objects, and you arrive at a cat sealed in a box with a fragile mechanism and a speck of radioactive material. If the atom's decay is probabilistic and unobserved, then the mechanism is too, and the vial, and so the story goes, the cat, alive and dead, becomes a single hyphenated word the mind recoils from. The tale was meant as a pointed joke, a protest against careless language. Reality does not show us cats in limbo. Something in the chain from the atom to the animal appears to force a choice. Physicists did not throw the story away. They kept it and argued around it. Some said collapse is real, a special process that happens when information is amplified to the scale of the world we inhabit. Some said nothing collapses at all. Every allowed outcome occurs, each in its own branching history. And what we call the outcome is simply the branch we are in. Others sought hidden variables, a deeper layer of mechanics that would restore definite properties all along. The interpretations differ like styles of poetry. The experiments, so far, keep the same beat. The Schrödinger equation remains the instrument. Its predictions keep matching what detectors click and plates record. From this mathematics, we learn that electrons can tunnel through barriers that classical logic forbids, appear on the far side with a probability that depends on the barrier's shape and width. We learned that two particles can become entangled, their properties braided so tightly that measuring one changes your knowledge of the other instantly. No matter the distance, no signal crossing space, just correlations that snap into place when questions are asked. We learned that atoms are stable, not because electrons whirl too fast to fall in, but because their wave-like nature and the uncertainty principle conspire to keep them from shrinking past a certain scale. A pressure born of confinement pushes outward as surely as any spring. The nuclear heart, once it was named and weighed, raised a different kind of question. Protons share positive charge and should repel one another with a vigor that would tear any close-knit cluster apart. Yet, nuclei hold. Neutrons, discovered with quiet certainty by Chadwick, help with mass and stability, but bring no electric glue. There had to be a force deeper than electromagnetism, one that only flexes its strength over vanishingly short distances and then relaxes to nothing. The strong nuclear force stepped into that role, not a whispered correction, but a dominant hug when protons and neutrons are close enough to touch. To describe such interactions, a new viewpoint came into focus. Instead of treating particles as tiny beads moving through empty space, we began to see fields as the true furniture of the universe. A field fills space the way temperature does, a room there at every point whether or not anything is passing through. A particle becomes a ripple, a little packet of vibration in its field. Electrons are ripples in the electron field. Photons are ripples in the electromagnetic field. Protons and neutrons are composed of quarks, ripples in quark fields, held together by gluons, the ripples of the strong force field. This is quantum field theory, not a new alphabet so much as a new handwriting, one that writes interactions as exchanges of quanta between fields that never leave the stage. The poetry sits comfortably with the pragmatism, calculations that would be impossible if you followed every imagined point particle can be made when you count ripples instead. The strong force, in this language, explains why protons are stable and heavy, why neutrons decay only on their own but live contentedly inside a nucleus, why the deep interior of matter is a crowded, lively place. Electromagnetism, written as a gauge field, explains how light is both wave and photon without needing to switch masks. The weak force, faint but essential, accounts for certain decays and the alchemy that runs stars. Gravity waits with patient dignity at the edge of this family portrait, welcoming geometry rather than quanta in our best current understanding, and inviting a unification the world has not yet yielded. None of this cancels the modest lesson that opened this stretch of night. The observer and the observed are not cleanly separate at the scales where quanta rule. Measuring is a kind of touching. Touching changes what is touched. The wave function is not a lie about a hidden classical world. It is a faithful language for a world that will not give you both position and momentum with perfect grace at once. The uncertainty is not noise you can sweep away with better instruments. It is the hum of the fabric itself. And yet, the hum carries harmony. Atoms form shells that fill according to simple counts, and chemistry blooms out of those counts with periodic regularity. Molecules keep to angles that can be drawn and predicted. Crystals repeat patterns in quiet lattices. Stars fuse elements by climbing a staircase of possibilities, rung by rung, until iron rings the bell. The world's solidity is a chorus sung by probability, not in spite of it. Let a small picture settle behind your eyes before they close. A faint cloud around a nucleus, not a smudge, but a map of where an electron prefers to be found when asked. A short equation that shepherds that cloud through time. A cat that never needed to be both alive and dead to make its point, reminding us instead to be careful with how we connect small systems to big consequences. A field everywhere, sleeping until a ripple wakes it. A proton as a bundle of buzzing quarks, none of which exist alone outside the hive. A force that is weak at long reach but mighty at a kiss, holding the nuclear family together. And you, at a human scale, where the uncertainties are gentle enough to let a cup sit steady on a table, where the same quantum principles that limit knowledge also make the table possible. The night, does not ask you to master the algebra. It invites you to trust the posture. Accept that questions at small scales have different shapes than questions at large ones. Accept that sometimes the best you can say is likely here, likely then, and that this is not a failure, but a full answer. Accept that your act of looking is part of the story the world tells about itself. From that acceptance, a richer clarity arrives. Circuits work, lasers whisper. MRI machines tune to the song of hydrogen in your body. Clocks that listen to atoms keep time so cleanly that continents can be mapped by their drift. Encryption keys grow from the impossibility of copying unknown quantum states without leaving smudges. The journey inward did not end with atoms or with electrons as clouds, and it does not end with fields, but the path is walkable and kind. It lights itself as you go, probability rippling into pattern, uncertainty laying boundaries that protect as much as they limit, equations that hum the same tune tomorrow as they did today. The observer is not outside the universe, staring through glass. The observer is a participant, welcomed by rules that anticipate the touch. In that welcome, doubt becomes gentleness rather than panic, and the smallest world becomes a place where you can rest your attention and feel, for a few quiet breaths, that you are learning to listen in the right key. Fields don't sit still. They can mingle, hum in harmony, and when stirred just right, briefly toss up tiny ripples that behave like particles. In this field-first picture, forces don't push like billiard balls. They converse. Two electrons repel, not by shoving directly, but by trading a messenger. An evanescent virtual photon that leaps between them, delivers its polite, "Please keep your distance," and vanishes. Virtual means borrowed time, a brief, rule-abiding appearance that lasts just long enough to carry influence and then slips back beneath the vacuum's surface. The strong force works the same way in spirit, though its messengers carry a more muscular tune. They're called gluons, earnest, literal, and wildly effective at their job. Follow those messengers into the heart of matter, and the story deepens. Protons and neutrons, once thought fundamental, are lively rooms packed with smaller guests. Three quarks, up and down in everyday matter, sit inside, but the space is never quiet. Gluons flit, tug, and trade, color charge, a bookkeeping label for how the strong interaction organizes itself. The colors aren't colors you can see. They're tags that keep the math honest and the particles faithful to the rules. Quarks come in a small family of flavors: up, down, strange, charm, top, bottom. A proton holds two ups and a down, a neutron, two downs and an up. Around and between them, gluons weave a net so tight that quarks never escape alone. Confinement is the strong force's signature, overwhelming within a proton's tiny breadth, almost absent beyond it. Think of a bodybuilder who lifts mountains at arm's length and refuses to budge outside the doorway. The strength is staggering, far greater than electromagnetism or the weak force, yet finicky about range, and the interior never quite settles. Even in calm matter, fields seethe. Virtual particles blink into being and out again. Quarks and gluons exchange momentum like quick notes passed across a crowded table. That bustle extends beyond the nucleus. Physicists kept finding more players. Muons heavier than electrons, neutrinos almost weightless and ghostly, pions and kaons, ferrying the strong force between nucleons. A whole menagerie whose names once sounded like a nursery rhyme and a thunderstorm colliding. It was charming and chaotic until a cleaner map arrived. The standard model gave the zoo a tidy home. Quarks and leptons became the building blocks, force carriers, photons for electromagnetism, gluons for the strong force, W and Z bosons for the weak handled the interactions. The Higgs field settled into the stage itself, endowing many particles with mass by the way they move through it, and its quantum, the Higgs boson, was finally seen in 2012. A shy crest in a sea of data, confirming a long-held suspicion. With this framework, predictions sharpened, experiments nodded, equations learned to sing in tune with detectors. It's hard to exaggerate how well this model works. It is not the whole sky. Gravity stands outside the tent. Dark matter and dark energy still wave from the hills, but within its domain, the standard model is crisp as winter air. The deeper lesson is gentle. Particle is a way a field behaves. An electron is a ripple in the electron field. A photon, a ripple in the electromagnetic field. Forces are stories. Those ripples tell one another by tossing quanta back and forth. A proton is not a single brick, but a storm. In a teacup, quarks and gluons, trading color with a ferocity that writes most of the proton's mass from motion and binding, not from the quarks alone. Even the tip of your nose is busy beyond comfort. Trillions upon trillions of virtual exchanges every second, all while your face sits there politely in the lamplight. From the search for smallest pieces, we arrived at a landscape of patterns and conversations, not things, but relationships, not silence, but organized murmurs that hold together as wood, water, bone, light. The more closely you look, the more the world resembles music, themes repeating, harmonics stacking, brief solos flaring and then rejoining the ensemble. Out of that hum, the tangible rises, tables steady under cups, trees storing sunlight, stars stitching elements, you taking a slow breath. Eventually, the questions turned from what's inside to what happens if we pull. The atom, understood in outline and in whispers, also carried astonishing energy. Not warmth like a candle, but power dense enough to light a city or flatten it. Fission was the first harsh revelation. A heavy nucleus, uranium or plutonium, can be made uneasy. Add a neutron, and it wobbles, divides into smaller nuclei, and releases energy plus more neutrons. If those neutrons find other heavy nuclei, the pattern repeats, a chain that either roars all at once or is tamed into a steady simmer. The arithmetic is stark and elegant. The products weigh a bit less than what you started with, and the missing mass becomes energy. E equals mc, 2, with C so large that even a tiny mass loss blooms into astonishing heat. In late 1938, careful chemistry met new physics. Bombarding uranium with neutrons produced fragments no one expected. The insight that followed, articulated in exile, on paper, with courage, was that the nucleus had split. The door swung open. In wartime, urgency took the lead. A secret project gathered minds and metals, ratios and risks, to build devices that would unleash a chain reaction in an instant. When those devices were used, entire neighborhoods became shadow and wind. The shock ended a war and began a reckoning that still hasn't found a final paragraph. Knowledge isn't neutral once it can choose how to arrive. The same reaction, slowed and moderated, boils water with exemplary patience. In a reactor, control rods sip excess neutrons. The chain continues at a measured pace. Turbines turn, lights stay on. No carbon flows from the chimney. The waste is quiet in the short term and difficult in the long term, asking for storage on timescales that exceed ordinary politics. Accidents are rare, but they echo louder than their statistics. Their names become shorthand for cost and caution. Even so, where the grid is hungry and the air is already heavy, a well-run plant can be a hard, honest ally. The other path traces the sun's method. Fusion presses light nuclei together hydrogen into helium and finds energy in the tighter binding of the product. Stars do this with gravity's steady hand. Crush the fuel, heat it until protons can handshake through the weak force. Let the strong force take over and hold the new nucleus. The idea of doing such work on Earth is as old as wonder. Gather a pinch of starfire, keep it caged, turn it into electricity with no long-lived waste and no chain reaction to run wild. The catch is temperature and control. A plasma must be hot beyond analogy and persuaded to hover away from any wall by magnetic fields shaped like bent halos. Tokamaks and stellarators hold that dream in steel and superconductors, confining a sun-hot donut in midair. Shots and pulses have worked. Net gain milestones flicker into reach and then retreat. The work continues with patience and international hands. Fusion has already proved itself in a more brutal register. A fission trigger can light a fusion core, and the yield leaps by orders of magnitude. Those devices redrew the map of fear for a generation, and the world learned a grim balance that depended on restraint. The paradox of nuclear knowledge crystallized. The same equations that promise a clean dawn can cast a long shadow at midnight. Out beyond the headlines, quieter benefits accumulate. Radioisotopes trace blood flow and metabolism. Radiation treats cancers with beams that know their targets. Sterilization and scanning keep equipment and bridges safe. Radiometric dating reads the ages of bones and stones from the slow ticks of decay. Inside hospitals, in labs and factories, the nucleus serves with humility. The power to shatter does not erase the power to mend. Even as utility grows, the open questions remain. The standard model leaves gravity on the doorstep. Dark matter tugs on galaxies, but not on our detectors. Dark energy leans against the expansion of space itself, and we barely have a metaphor. The constants of nature are what they are. We don't yet know why they chose those numbers. Whether deeper symmetries hide beneath today's elegance is an active whisper. Whether space-time and quantum fields meet in a single grammar is a patient argument between the chalkboard and the sky. For tonight, the shape is enough to hold. Fields pervade everything. Particles are their ripples. Forces are conversations carried by quanta that may be real and long-lived, or virtual and brief. Protons are not pebbles, but braided storms. Atoms are busy rather than solid. Energy hides in binding and can be coaxed out by splitting or squeezing. The visible world gathers itself from invisible traffic, a choreography measured in femtometers and attoseconds that somehow builds forests, oceans, laughter, and rest. Let the imagery lean close while your eyes grow heavy. Inside every nucleus in your body, quarks trade color under a rain of gluons. At the edges of every atom, electrons lounge in cloud-shaped rooms whose walls are probability. Between nuclei, photons, and virtual photons keep the peace by reminding charges where they stand. In the background, the Higgs field lends heft without asking for attention. The end of your nose is quiet to you because all of that motion adds up to reliability. The table holds. The glass does not shimmer out of existence. The lamp hums with a current that owes its life to quantum rules. The night outside is lit by fusion, running on a timetable written in stellar cores. We did crack the atom. We learned what flies out when it opens, and we learned what can be done with that flight. Some muses ask for grief and vows. Others ask for careful optimism. The responsibility is ours and cannot be set down. Curiosity keeps its wings. Caution keeps a hand on the tether. Between them is a path worth walking. Power plant instead of blast. Healing beam instead of harm. Detectors that listen for neutrinos pouring from the sun, confirming that stars are doing exactly what the equations promise. What began as a search for a smallest, simplest bead became an invitation to understand patterns, whispers, and wiggles arranged into rules. Even where the map says, "Here be dragons," the parts we do know are sturdy enough to build with. The fields keep playing. The forces keep their manners, and under all the motion, a human truth. We opened the atom, and it did not close behind us. It asked us to grow into our knowledge. It asked us to balance heat with light, ambition with restraint. It asked us to listen longer, measure more gently, and choose what kind of world we want to assemble from the ripples we now know how to stir. Set the thought down here. In the quiet beneath your breath, imagine that busy interior slowing to a lullaby. Virtual particles blink and are gone. Gluons finish a frantic loop and settle for a moment. A magnetic bottle in a far laboratory holds its shimmering ring and then dims as the pulse ends. Somewhere, a reactor lowers its control rods by a millimeter and the heat steadies. Somewhere else, a therapist shapes a radiation beam to the curve of a tumor and turns a knob with deliberate care. From the smallest exchanges to the largest decisions, the same lesson repeats. The universe is built from conversations. We have learned to join them. May we keep our voices soft. In every reactor core that hums, in every medical isotope that glows faintly behind thick glass, in every fusion device trying to teach a tiny star to hover, the heart of the atom keeps its quiet fire. And we, the curious apes who leaned close and dared to listen, have to choose how that fire is kept. Not long ago, atoms lived mostly in the margins of notebooks and the corners of lecture halls, ideas in sandals and chalk. They were elegant guesses wrapped in Greek words, neat circles on a slate, little nouns for the invisible. Now they answer to gloves and clean rooms. They sit under microscopes that can feel a single ridge on a single atom. They ride inside machines that map the body's interior without a knife. They open doors for bits of information that are not quite zero, not quite one, and sometimes both at once. The small, once only imagined, is now an instrument we tune. Look around the room. Somewhere within reach there is a device that learned to speak because we learned to listen to silicon. Semiconductors are not simply materials. They are neighborhoods for electrons, streets and intersections built from energy levels. Pure silicon is polite but shy. It conducts only under certain conditions. Add a whisper of phosphorus here, a hint of boron there, and the neighborhood changes. These tiny additions doping create places where electrons are eager to go and places where they are missing and would like to be. On a slice of crystal thinner than a fingernail, engineers etch whole cities of transistors, each one a gate that opens or closes to guide current. Millions turned to billions, then trillions. Music streams because electrons choose the paths we planned. Spacecraft steer because a bit flips when invited. This is not casual chemistry. It is patient carpentry at the edge of the possible. Carpentry that works only because electron bands and atomic impurities play by quantum rules. Step into a hospital, and the atom changes masks again. In the tunnel of an MRI machine, a magnet's deep, steady field coaxes the tiny magnets of hydrogen nuclei into alignment. A carefully timed radio pulse tips them from attention. As they relax, each nucleus whispers a small signal. Together, those whispers build a picture-soft tissue, drawn without a blade, blood flow traced without dye. The word nuclear sits inside MRI like a quiet truth. We are listening to the nuclei of atoms. No radiation baths, no sparks, just the magnetic personality of hydrogen, abundant because water is abundant and you are mostly water. Knowledge that could have built only weapons found a gentler occupation. Diagnosis as music, a chorus of spins returning home. Elsewhere, in the same building, atoms work as messengers and healers. In nuclear medicine, a carefully chosen isotope joins a molecule on its errand, glucose to a hungry tumor, iodine to a needy thyroid, and reports back with a handful of decays. Detectors around the patient read those reports and assemble maps of metabolism and motion. Sometimes the isotope does more than speak. Sometimes it acts. Radioactive iodine calms a runaway thyroid. Gamma beams and proton beams, shaped with computer care, deliver doses to tumors that would be unreachable by scalpel. The energy in the nucleus, the same intimacy that powers stars and haunts our history, becomes a scalpel of light. The frontier does not stop at imaging or therapy. It shrinks further until a billionth of a meter feels like a boulevard. Nanotechnology begins where ordinary intuition loosens its grip. At this scale, surfaces matter more than volumes. Van der Waals forces soft attractions between molecules gain a vote. Gold dust stops looking gold and starts looking crimson or violet. Carbon reimagines itself as nanotubes stronger than steel, or graphene sheets that carry current like 1,000 tiny highways stacked flat. A material can be designed not by blending in a vat, but by carving a landscape atom by atom so that water beads and rolls, or a crack stops instead of running. In one lab, a scanning tunneling microscope drifts a needle just above a surface and feels a single atom's presence. In another, arrays of nanoparticles carry drugs to cells by reading proteins like street signs. What once sounded like magic belongs to a craftsperson's bench now. A steady hand, a steady signal, and practice. Push a step further, and the rules themselves become tools. Traditional computers live in a strict neighborhood. A switch is on or off. A bit is 1 or 0. The quantum world lets you hold a bit as a cloudy both until you look. A qubit. Build one from a trapped ion, an atom caught in an electromagnetic net, and use lasers to nudge its internal states. Build another from a superconducting circuit current, flowing forever, without losing heart, and let microwaves coax it into superposition. Entangle a few qubits so that a change in one reshapes your knowledge of another, no matter how far apart the hardware sits, and you have a logic that ordinary machines cannot mimic efficiently. It is delicate work. A cough of heat or a stray vibration can scatter the careful quantum choreography. Error correction schemes act like guardians, catching mistakes before they spread. The progress is spiky and real. Algorithms that factor, search, simulate, prototypes that grow in qubit count and calm, ideas that were chalkboard fictions, becoming devices that demand plumbing diagrams. Under every scheme is the same lesson. Atoms and fields are not just subjects of study. They are components in a new kind of instrument. Meanwhile, a quieter chorus of atomic techniques hums in the background of everyday life. Food and medical tools are sterilized by measured radiation that kills what would harm us while leaving the useful untouched. Plant seeds meet discrete doses to encourage variations that can weather drought and salt. Archaeologists hold charcoal or bone to a detector and read the slow fading of carbon-14 to date the campfire or the burial. In the sky and below it, atomic clocks count time by listening to the precise tick of cesium or rubidium. That tick is so steady that it can catch the sag of Earth's crust and the drift of continents. It guides spacecraft between worlds and tells your phone when to turn left at the cafe. A probe far from home listens to the same atomic rhythm to fire thrusters for a half second and thread a gravitational needle. These devices do their work without drama, precise because atoms are precise. All of this rests on a shift in how we think. Atoms are no longer only what things are made of, they are platforms. A dopant atom is a valve. A lattice of atoms is a detector. A single defect in diamond, a nitrogen vacancy center, becomes a tiny magnetometer that can read the field of a single neuron's whisper or the stress inside a crystal. A ring of superconductor becomes a qubit's quiet home. A cloud of ultra-cold atoms becomes a simulator that mimics the behavior of materials we can't otherwise build. Possibility replaces mere composition. We ask not only, what is it, but what can it be persuaded to do? The language adjusts. Probability clouds become diagrams that engineers use to place gates and wires. Tunneling stops being a curiosity and becomes the way a flash drive stores your photos. Coherence, the fragile alignment of phases in a quantum state, stops being a philosopher's toy and becomes the budget line on a lab's whiteboard. How many microseconds before the useful fuzz falls apart? Spin leaves the blackboards of the 1,930 seconds and walks into MRI suites and qubit chips. The atom, once a noun, becomes a verb. Even in fields you wouldn't expect, the small keeps showing up with large effects. In agriculture, measured irradiation keeps food safe without heat or chemicals. In industry, radiography checks welds deep inside steel without cutting, and ion implantation scribes the properties of materials with surgical precision. In space science, tiny ion thrusters, fed by noble gases and tuned by electronics that reason in electrons and lattices, whisper a steady push that over months becomes a new orbit. Everywhere you place your attention, the same story reappears. Control at the atomic scale leads to capability at the human scale. So here we are, living inside a world built from the inside out. The chips in our pockets, the scanners in our hospitals, the coatings on our fabrics, the instruments that keep planes apart in the night, all of them hum with atomic elegance. Democritus's quiet guess has become the infrastructure of modern life. The atom grew more real and more abstract at once, more solid in the way it behaves in bulk, more slippery when asked to sit still and be a thing. It isn't the bottom brick, it's the doorway into rooms below. This is not triumphalism, it is tenderness. The more we have learned to do with atoms, the more we have had to learn about ourselves. The same reactors that glow cleanly on a riverbank are cousins of the devices that cast long shadows in history. The same imaging technique that maps a child's brain with kindness flows from the same set of principles that can split a city's morning. The atoms never choose their purpose. We do. That choice is renewed every day by people who pull levers and write code and sign permits and turn keys. Wisdom has to keep up with cleverness. What the atom taught along the way has a way of slipping into the rest of life. Invisible does not mean empty. Uncertainty is not failure. It's a boundary. that guides better questions. Small things rule large outcomes when they are arranged with care. Structure can arise from a base that looks like noise if you are too far away to see the pattern. Those are physics lessons. They are also ways to be gentler with each other. Close the circle for a moment. The word we inherited, atomos, meant uncuttable. We cut it anyway and found a nucleus. We opened the nucleus and found protons and neutrons. We looked inside them and saw quarks and gluons. We stepped back and noticed fields everywhere, knitting reality so thoroughly that even empty space is busy. Virtual particles flashed like brief fireflies, their comings and goings constrained by rules we wrote down after watching carefully for a century. Somewhere along the way, we stopped looking for a final, quiet bead and started listening for patterns. The atom became a story with characters who share lines. If you could draw the tale, it would look like a score, notes and rests, dynamics that swell and fade, themes that return in different keys. And still, the world holds. Atoms gather into molecules, molecules into cells, cells into organs, organs into bodies that move through rooms and feel the breeze. Your breath tonight is a choreography of atoms, oxygen folded into hemoglobin, carbon dioxide released from 1,000 small furnaces, water tracing its slow cycles through tissues that repair themselves as you sleep. Each inhalation is a treaty between chemistry and biology signed under starlight. Those stars forged much of what you are in old cores and violent endings. Their dust wandered and cooled and learned for a brief time to call itself you. The smallest things, it turns out, are not simple. The invisible is not empty. The questions we keep asking, what is it made of? What holds it together? What hides underneath? Are the same questions that pushed a Greek along a shoreline and a student into a lab at midnight and an engineer into a clean room at dawn. The answers have grown stranger and kinder. We build with probability now. We shape with fields. We treat information as something nature stores in phases and spins. We are learning to dream in the grammar of the small, and to make those dreams useful without letting them become unkind. Let the thoughts settle as the room quiets. The phone at your bedside is a conversation among doped silicon, metal gates, and electrons that tunnel without permission. The clock in your pocket keeps time by listening to an atom's steady beat. The light that warms the pillow is a long echo of fusion that began before you were born. Somewhere, a quantum device holds a handful of qubits in fragile agreement, doing a calculation that would have sounded like superstition to your grandparents. Somewhere else, a nurse slides a patient into a magnet, and hydrogen sings the body's shape. Somewhere, a reactor lowers its control rods to meet the evening's demand without smoke. All of it is the same story. Whispers leveraged into wonders, small rules assembled into shelter. The atom remains what it has always been, a cornerstone and a mystery, a tool and a poem. We keep learning how to speak with it gently, precisely, with a respect that comes from knowing how easily cleverness outruns care. And as you drift, remember the simplest, bravest truth. You are made from the same vocabulary you study. Hydrogen and carbon, oxygen and nitrogen, a little iron to carry breath, a little calcium to carry weight. Fields and probabilities arranged into a person who can listen for the faint hum beneath everything and feel comforted by it. Sleep, then, inside that music. Let the mind float over silicon valleys and magnetic tunnels, over lattices and orbitals, over clocks that count the seconds with the steadiness of stars. The universe is not a machine. It is a quiet song, and atoms are its notes. Night gathers them into chords and hands you the melody. In the morning there will be more to learn, more to build, more choices to make about how we tend the fire. For now, breathe. The small will keep doing its careful work,